isolate the tone and do that calibration then. Because they won't be sharing the same hello, and then you can adjust the phase in that manner. So that's a cool trick we can do again. Okay, thanks.
All right, just before lunch, we've got another presentation from Justin Ford. He's going to be talking about liquid DSP. Just for a few minutes here and talk about actually two topics. So John referenced liquid DSP, which was an effort that took place during Hackfest, and I'll have just a brief excursion on that. But the preponderance of what I'm talking about today is actually to do with using digital signal processors as hardware accelerators. And the work that's represented here was done by a team of folks at San Diego National Laboratories. I'm just here representing that team. Also from the team here at the conference is Adam Goldhammer. And just a brief note here that the presentation additionally represents the work of Sandy, a lawyer. So you can see a variety of disclaimers on the cover slide. And those, will be a few of those also replicated throughout the presentation. So just a bit of background about what motivated the, what motivated us looking into digital signal processors. What we were really interested in doing is looking for a path towards low power software-defined radio. And I'll get into a little bit why we think DSPs enable that. Before I do, I just want to emphasize why we chose the particular approach we did. I think if you imagine for a moment digital signal processors and low power SDR, one of the products that might come to mind is the Texas Instruments OMAP, which is featured in the EDIS E100, and there's a picture of it up there on the gum sticks board that carries it. There has been some work done looking at trying to use that kind of system on a chip with relatively limited DSP resources, particularly Al Fayez's master's thesis at Virginia Tech sort of documented his exploration of it. And it turns out that it's relatively difficult to use the DSP as it's integrated in the OMAP. It's also a relatively low power part, low performance part rather. And so what we wanted to do was look at a little bit higher performance digital signal processor and just try to examine whether there's a particular advantage to using digital signal processors, both in GNU Radio and just in general as an accelerator for software-defined radio. And so what we did is got a multi-core DSP system on a chip from Texas Instruments. This is a commercial product. They produce an evaluation module, which is relatively inexpensive, a few $100s. And they also provide a carrier card that connects through PCI Express to a standard desktop computer. And so this provided us with a prototyping platform, which is what I'll be describing for the remainder of this presentation, where we can look at DSP performance and use GNU Radio as a framework to examine how that would operate in a software-defined radio. But before I get into it, I just want to sort of highlight that the real path to applying this kind of work is to pick some sort of low-power standalone platform that includes digital signal processors. So what I'm describing today is really how you explore this space and how you examine what the value of the coprocessor is. But really where you want to look for using this is more towards some of the newer TI products that include multiple ARM processors as well as multiple DSPs, or recently Qualcomm's announced a software development kit for their own DSPs, which are very low power and high performance. So what does it mean to have a coprocessor in GNU Radio? We've seen a couple of slices of this sort of overview in previous presentations. I just want to give kind of a high-level perspective of what a generalized approach might look like. So you have an example notional flow graph here, and there's some source of data and some sink you're sending it to, and potentially 3 functions in that flow graph that are performing some kind of signal processing. If you want to offload some of those functions, what you're needing to do is break the flow graph and insert some blocks that represent the offload. And there's a couple of things that have to happen in order for this to be successful. The first is you have to move data from the host PC that's running GNU Radio down to the coprocessor. In our case, we call that an egress function. You're sending data out of the host down to the coprocessor. And then you need to chain together the same operations, but they're implemented on the coprocessor in this case. So you have some kind of representation that's sitting down on, in our case, a DSP, or perhaps on an FPGA or a GPU. And you chain those together just like you had in the flow graph above, and then you need to move data back up to the host PC. A detail that can be easy to overlook when you're just sort of glancing at this is somehow the coprocessor needs to know when to run function A on what data, because this is streaming, right? This is a real-time operation. And so there's constant interaction between the host PC and the host coprocessor if you want to leave the GNU Radio in charge. And that's what we did. And I think as a community, that's probably what we're driving towards. Just a brief note before I leave this slide. If you guys saw the GRGPU presentation at a previous GNU Radio conference, the approach that was used there for using GPUs from the group of Maryland is quite similar. In fact, we were in conversations with Will Blisker, the developer of GRGPU, on this concept. So I just want to right up front kind of throw up an example of using digital signal processors to do meaningful functions in GNU Radio. So this is a screenshot of an actual flow graph. And instead of being notional, now we actually have something like a UHD block and maybe a GUI sync to look at the spectrum. And here's our egress block that moves data from the host to the DSP, and the ingress block that moves data from the DSP back to the host. You'll notice that blocks are parameterized, so in the case of egress and ingress, there's two parameters. One that sets the amount of data you move each time that the scheduler calls egress, and the other is just a reference to the DSP kernel mode driver. And then I've just got a few functions here to represent some of the things that we've implemented on the DSP, and these blocks are also parameterized so that things like filter coefficients can be passed down at runtime. So let's peel back just a layer of abstraction here, kind of underneath what's happening from a flow graph, and think about the interaction at a hardware level. On the left-hand side of this chart, I'm just showing what we normally think of as a GNU Radio setup. There's some kind of RF front end. There's a multi-core Intel machine, and it's running the GNU Radio framework. What we've done is we've added an interconnect between that machine over to this digital signal processor system on a chip, which is also a multi-core machine. And we have implemented a variety of functions, which I call optimized kernels, that are placed in the DSP firmware and callable from the host computer. So over this high-speed interconnect, which in our case is PCI Express, you can send commands to perform certain operations at certain times, and you can also pass data back and forth. This is a picture of the actual system on a chip board, and sitting down here underneath the notional representation of the computer and the DSP are sort of rough order of magnitude performance and power numbers. And I think this helps motivate why we were interested in using the DSP to accelerate functionality for software-defined radio, because you get kind of an Intel class machine, that's the Sandy-Bridge Xeon part that I'm using there as a reference, and about an order of magnitude less power. So how do you achieve that kind of performance? What is it that's magical about the digital signal processor? This is the system on a chip block diagram from TI for the part that we used. There's some information here on the right representing the PCI Express performance. There's a picture of the peripherals sort of down here. Also a note that this part performs, supports single precision floating point operations, which we leveraged. And then some other notes that you can read. I do, though, want to say a few things about the particular DSP core's performance that may not be familiar to some of you. So DSPs are highly parallelized architectures. There's actually, in this particular, each core in this part has 2 execution paths, each of which has 4 function units. And it's also a very large instruction word architecture, which means that a single instruction on each clock cycle can specify up to 8 operations to be performed on multiple data from any of the registers that are available in the part. It's also pipelined between 7 and 12 stages, depending on the operations that are have been requested. And so the parallelism and the ability to do SIMD operations is really what makes DSPs very well suited to do signal processing, in addition to their very high multiply accumulate performance, which of course is relevant to filters and that sort of thing. So how did we actually connect the performance of that DSP to GNU Radio? The diagram here shows just notionally that system on a chip with the 4 DSP cores, and the idea that there's a PCI Express bus out to the host PC. What we needed to do is create a way for the user space application, GNU Radio, to ask the DSP to do operations that it's capable of performing. And so we made a job queue that the kernel mode driver manages, accepts requests from user code like GNU Radio, and the DSP then can retrieve those jobs and the corresponding data and perform operations on them. So we have the host PC in charge, which allows us to continue to use the GNU Radio scheduler as being the decision-making entity for when to perform which operations. This is a representation of execution flow using the digital signal processor in GNU Radio. There's kind of this notional block diagram on the left-hand side here with an egress block function and an ingress block. I put some broken lines in between egress and the function, and ingress to indicate you could have multiple operations taking place. And what this flow graph is telling you is sort of in columns the different layers of our system. So here's GNU Radio, which can make ioctl calls to the kernel mode driver. And the driver, of course, operates over PCI Express between the computer and either the DMA engine that's on the DSP for transferring data, or directly with the code running on the DSP in order to perform operations. So importantly, you can actually transfer data without interrupting the DSP's operation. That's an independent process. And then once you've got data down there, the GNU Radio block requests an operation by passing a job structure and sending an indication to the DSP that a job is being requested, and next time the DSP has available time, it will perform the operation on the corresponding data. Once it's complete, the DSP notifies the host that the operation is done, and the driver can tell the GNU Radio block that that operation is completed, which of course informs the scheduler that another operation can be performed, or the data can be transferred back if that's the last DSP block in the chain. So I mentioned that this is a prototyping platform. We wanted to look at what's the performance of DSPs when you have these available kernel operations and you want to chain them together to perform SDR operations. So the next few slides are about benchmarking the DSP configured this way. And shown on the left here is pseudocode of the benchmarking that we did, where we looped over a couple of parameters. One is the number of host side threads that are simultaneously making requests to the DSPs to fill up that job queue. Another parameter was the amount of data that you transfer each time the operation is called. And then inside of that, over 1 million samples, we executed a single function just to measure its performance in aggregate. It collected mean statistics on the amount of time it took to, for example, write data out or to perform the operation or to read data back. So that produces these kinds of plots that are three-dimensional, where we're showing the third dimension as a color map. Looks a little busy, but I can explain it fairly quickly here. The vertical axis is that transfer size. It's represented in log2 space with 128 samples at the minimum, 64K samples at the max. The horizontal axis is the number of host threads that are requesting jobs from the DSP. And then the color intensity represents overall throughput for the particular operation that is being timed. So this chart shows on the left-hand side an egress writing data down to the DSP, and on the right-hand side, an ingress reading data back from the DSP. There's just a couple of features I want to point out here quickly. The first is that as you increase the amount of data that you're transferring on each request, performance gets better. And the reason for that is that the bus overhead is becoming a smaller proportion of the overall operation that you're performing. Another feature to note is that once you move away from a single thread, the performance per thread adding threads on doesn't actually change the performance very much. It's pretty flat out there. And the reason for that is that when you're just measuring how long it takes to write or read back, the bus is actually really busy. And so adding more requests on doesn't improve throughput. These charts are a little bit more interesting because we're actually looking at the performance of particular operations. And the case here, we're on the left-hand side, this is like a no-op. We just write data down, read it back, and measure the overall throughput for all million samples. So it's the average of all 1 million samples. The axes are the same on the transfer size and the thread count. The other operation we looked at was performing a fast Fourier transform. And so now here you see more interesting patterns. On doing a loop back, you just sort of kind of see the trend of the larger the chunk size, the better the performance, because you're really bus constrained, just trying to move data back and forth. There's a little bit of an advantage potentially for adding on some host threads because you might marginally increase the overall busyness of both transferring to and from the DSP. If we look at actually performing computation on the DSP, note the relative change in the magnitude of the overall throughput. It's expensive to perform an operation relative to just transferring data, so that shows up in how much you can actually push through the DSP. And there's also interesting shaping here. So initially you see that as you increase the chunk size, performance is getting better, but then it begins to go back down. That's because the FFT size is determined by the transfer chunks. The FFT operation is actually getting more expensive here, more data to push through. And you see an interesting peak sort of over towards 10 threads, which is the maximum size of our job queues. So it seems that this particular DSP likes to perform 4096 bin FFTs, and this sort of chart then informs the trade-off for incorporating a coprocessor into your SDR system. You know where you want to target the amount of data that you're moving to and from the coprocessor, and how to think about how operations perform within the context of incorporating the coprocessor in the system. So I just want to briefly break out the presentation here and show a video of building up a flow graph using the DSP. Okay, so here's the familiar GNU Radio companion, and what's going to be done is just putting together a simple flow graph that tests the functionality of the DSP operation to make sure that data integrity is maintained. So a few variables are being set up here. For example, the transfer size of 4K samples is going to be specified. And then next, dropping down some standard GNU Radio blocks. So we did not modify GNU Radio to do this work. We just made an out-of-tree module. So these blocks that are coming down right now are the same ones that you would get on your system using the standard GNU Radio release. Just going to use a signal source with a sinusoid and a couple of time domain sinks to look at the signal that's put into the DSP chain and the difference between the output of the DSP chain and the input. So now, down here on the right-hand side, there's a group of blocks that are related to our DSP implementation, from which the egress and ingress blocks are going to be pulled. These are the operations to move data between the host and the DSP. And then the operations being put down is an FFT followed by an IFFT. So the output of these two operations together should be the same as the input. Again, this is just a simple test to show that data is not corrupted moving through the DSP and having operations performed on it. So you just hook these up like you would normal blocks. You may have noticed the data type change from the input of the egress to the output of the egress. It's going from complex floating point to integers, and then the integers are passed between the DSP blocks. Those integers represent pointers to the data that's on the DSP, and the driver uses that to know which data chunk to specify an operation should be performed on. So now everything's all wired up, and the flow graph is going to be run. When the run button is pushed, the operation of GNURADIO looks the same because, again, this is just an out-of-tree module. And out comes an output that shows this is the input signal here on the bottom, and on the top is the difference between the input and output. That means 0 indicates that the data is not corrupted. And a few zooms were made there just to show that this is running in real time. So this is just a static image of the video I showed, and I just want to point out briefly that when this flow graph starts up and the constructor of egress block is called, that's when the driver is queried to determine what firmware is present on the DSP, and if the desired firmware isn't there, it can actually request that it be loaded before the flow graph runs. After that firmware is loaded once, then all of the operations that are defined in the blocks are present, and it's a runtime request to specify which operations perform when. Okay, so here's the two presentations and one brief aside on stuff that was done at the Hackfest. When I decided to go to the Hackfest, I took another member of the team that did this development, Kevin Malone, with me. And Tom Wando put forward the idea that maybe we could look at using a C library that has optimized DSP functions in it that was developed by Joe Gatter, who was just finishing up his PhD at Virginia Tech at the time. Postdoc. And there were two reasons why this was interesting. The first was to see if it would be possible to pick up some of the modules that were in Joe Gatter's library but hadn't yet been put into the radio blocks. There were a few examples of some forward error correction and other operations that looked interesting. The second motivation was that Joe had spent a lot of time looking at some fixed point operations which are not very well represented in GNURADIO. And so the interest was, can you wrap up the liquid DSP operations in GNURADIO blocks and have something functional? So what we decided to do was just pick a few simple examples of an FFT operation and an IIR filter so that we could prove that wrapping the liquid library didn't present any incompatibilities inside of GNURADIO. And we tested those out and found those were fine. Unfortunately, the version of Joe Gatter's library that he had up on GitHub at the time didn't have all of the fixed point functionality in it that he had developed. And so we didn't really get to look into that very much, but we did show that it's possible to use the liquid library inside of GNURADIO, and the out-of-tree module that we built is available on GitHub at the link provided there. In order to use it, of course, you have to have Joe's library, which is also freely available. So I just want to conclude briefly here with a recap of our work with digital signal processors, the motivation of having a path towards low-power signal processing if you have a system available with a DSP in it. We did our examination over a PCI Express bus, but that was really just to explore the nature of having these optimized kernels and calling them from within the radio. So you do this effectively, you really need a memory map to DSP, and to use the system on a chip from TI on your own board or on somebody's board that's developed around that product. There are, of course, other coprocessor concepts. And so I, at this point, would just like to plug the 11 a.m. working sessions tomorrow. There's going to be one on the topic of coprocessors in GNURADIO. And you probably have seen through all of the talks that have been presented so far, and I think there's one or two left, that there's a couple of considerations in how to actually incorporate a hardware accelerator inside of GNURADIO. One is how do you move the data back and forth between the accelerator and the host. Another is how do you decide which operations to perform in what order, and do you leave GNURADIO in charge from a scheduling point of view, or do you put the coprocessor somehow in charge of making that decision? And if all of that's set up, then how do you actually effectively utilize the coprocessor within GNU Radio? When should you call on it? Volt does a very good job of figuring that out for you to use the SIMD unit within an Intel processor. We don't really have a mechanism for saying, here's a good point in flow graph to apply a DSP, or here's a good point to use an FPGA. And so from a user point of view, today, applying a hardware accelerator adds a lot of complexity. We have a simplified way to bring the blocks in. We haven't yet answered the question of when should you do that. It's motivated in our case by low power applications, so probably for the heavy lifting is where we would do it. But for other coprocessors, there may be different occasions when we want to do it. So if you have an interest in exploring those topics and discussing them and trying to set the direction for GNU Radio on coprocessing, then 11 a.m. tomorrow we'll be coordinating a working session on that topic. Thank you. Yes?
So do you use DSP Live at all, or did you do everything with DSP Live?
So the question is whether I use a particular library to implement the DSP functions, or if we use the Texas Instruments compiler. So we did use TI's toolchain, and a bit of code they provided to us started our effort in developing the driver and the corresponding firmware to interface the DSP to the computer. But that code was written by electrical engineers, the sort of typical, main function, do everything, fix it. And Adam really dressed up the driver, added the stuff that we needed. In terms of implementing DSP functions, we definitely used the TI toolchain, and in some cases where it was available and made sense and was sufficiently parameterized, we also used some of their library operations to implement the directional. Absolutely. The library functions are highly optimized. They do take advantage of the parallelism and the pipelining appropriately, which can be a challenge for someone who's not familiar with this.
So in the Flex 6000 series, Flex Radio 6000 series, there's the